All right, welcome to Chapter 10, Section 3, Proofs with Parallel Lines. So just to remind you, as a little bit of background information, in Chapter 10, we're talking about parallel and perpendicular lines. Chapter 2, Section 2 and Section 3 both focus on parallel lines. And you're going to find a lot of similarities here in Section 3 to Section 2. They're basically flip sides of the same coin. And so the focus here is going to deal on proofs with parallel lines. Namely, the main point here is how do I prove lines are parallel? That's going to ultimately be the focus of this section. And what you're going to find is we're going to deal with the same four critical properties, same critical theorems as section 2, corresponding angles, alternate interior angles, alternate exterior angles, and consecutive interior angles. We're going to deal with these same properties, and they're going to have the same exact functions. Certain ones are going to be congruent, some are going to be supplementary. But the flip side of the same coin is going to be utilized here. Namely, in section 2, we started with parallel lines that were cut by a transversal. We started with parallel lines that were cut by a transversal, and because of that situation, those four properties had to be true. In this section, it's the flip side of the same coin. Now I know these properties to be true. In other words, I'm going to start with any one of these pieces of given information. So basically, if I start with now just two lines that are cut by a transversal, the transversal is still the same thing. The transversal is still the thing that crosses the H right here. These are the transversals in each of these cases. So when you see that word, that's what it's referring to. It's what crosses the H. Now, the two lines that are going in the general same direction, what we're going to find is we're going to have certain kind of features about the angle clusters that are created here. Again, there are two clusters of four angles that are created by these intersections. And based on the positions and the qualities of those angles, we're going to be able to show that the lines have to be parallel. And it's the same exact four properties. So basically, if corresponding same position angles, so bottom right in these two clusters, if those happen to be congruent, so again, the way I might see this in an example in this section, I might be given that this angle measurements 60 degrees. And if I'm told that that one's 60 degrees, what that means is that I now have corresponding angles that are congruent. Because of that fact, that's going to force the two lines to be parallel. So you'll notice the missing piece here that's different from section 2 is that I'm not shown those two little red arrows. So I'm not starting with the fact that those are parallel. But because of this fact, those lines have to be parallel. Pretty powerful piece. The reason why this is important is because what you're going to find, particularly in this chapter, is I'm not going to be really dealing with the coordinate grid all that often. And one of the features that we've been able to latch onto in the past is I can show lines are parallel by the same slope. Well, if I don't have a coordinate grid, I can't show anything about slope. This is a way to bypass that. So if I have information about the angles, I can now show these are parallel, which means they also will have the same slope. They will never intersect in the same plane. Okay, and the same thing applies here for alternate interior angles. In other words, diagonal inside angles across this transversal. If I can show these two are the same, so if that was 100 degrees and that was 100 degrees, because alternate interior angles are congruent, that's going to force these two lines to be parallel. Alternate exterior, diagonal outside angles. If I can show that these two are congruent, or those two, it doesn't matter. It just has to do with the position. So if that one was, say, 97 degrees and that was 97 degrees, because they were congruent or the same, that's going to force these two lines to be parallel to each other. And this one, this is the oddball, so make sure that you circle this one, star this one, because it's so easy to get used to this congruence, same, looking for the copy and paste, that this one tends to fly under the radar. Consecutive interior, or same side inside angles, if they are supplementary, and again, if you need to write down your margins, what that means, supplementary means they add to make 180 degrees. So for instance, in this example, this is not the only way to do it, but if I have these two angles add to 180, 110 plus 70 equals 180, if this happens to be the case, that's going to force these two lines to be parallel. And again, the main thing to emphasize here is that in each of these cases, this is the exact same set of four rules from section 2, but I'm just starting with different information. Section 2, again, I started with the lines being parallel, and that forced each of these facts to be true. In this case, in section 3, now I'm starting with these facts. I'm going to start with information about the angles, and that's going to, in turn, force the lines to be parallel to one another. Okay, so flip sides of the same coin. The convenient thing here is I'm still dealing with the same 4 rules. All right. Just to show you briefly, I'm going to do these 2 examples on the whiteboard in just a second, but these are what we're going to be doing in our notes. So let me jump to our whiteboard, get us set up right here. Okay. So our first example here is what you're going to be more commonly starting with. We're going to do one example from that because it's pretty much the same sorts of things that you've seen in section 2, and then we'll do a proof as well, which tends to be a little bit more of the tricky things, but we'll talk about what you'll see on big ideas for that. So in this first example, we're asked to find x. Now, what you're going to notice about the different phrasing here from section 2 is that in section 2, it started with the fact, all right, the 2 lines are parallel, and it would have shown you in the diagram those little red arrow things that show parallel. We're going to see that in the proof in just a minute, but you'll notice it's missing here. In section 2, it would have started with that fact, and then it'd say like, all right, now find x. Basically, because the lines are parallel, cut by a transversal, those 4 different theorems had to be true. Whatever the positions may be, I just used them to my advantage. In this case, you'll notice a slightly different phrasing. It says find x so that these lines have to be parallel to each other. There is only one value of x that's going to force these to be parallel. Any other value, they are going to intersect somewhere. Okay, it'll change the slopes of the lines and stuff. Okay, but the important thing, the more simple thing to latch onto here is that basically my job here is going to be use one of those 4 theorems again. Corresponding angles have to be congruent. Alternate interior angles have to be congruent. Alternate exterior angles have to be congruent. And finally, consecutive interior angles have to be supplementary. They have to add to 180. So based on the position of my angles here, I'm going to use these pieces of information to write an equation that's going to force these 2 to be parallel. So the trickiest part here, and again, in your assignment, you're going to see different variations about where the different angles are located, whatever they may be. You have 4 to choose from. You get to pick. Now this one's convenient. You'll notice that these are diagonal inside angles to one another. So I can use my alternate interior angles theorem. That's the second of those 4. And what had to be true is if these lines are parallel to one another, these 2 angles, the diagonal inside angles, the alternate interior angles, had to be equal to one another. They had to be congruent. So my equation I can start with here to solve for x is I can take each of those angles, 3x plus 5 and 65, and because they're congruent, they have to match. The way I write that mathematically, they have to equal each other. And now I have an algebraic equation. This is now a chapter 1 problem. It becomes solve for x. Distribute, collect like terms, move stuff away from the variable. Nothing to distribute here, so my job just becomes to start moving stuff away from x. Okay, so I'm going to move this 5 first. I would move that by subtraction, and so I get 3x is equal to 65 minus 5, or 60. Now to move the 3, it's multiplying by the x, so I'm going to divide my inverse operation to cross this bridge, and now I'm going to divide 60 by 3, and that's going to give me 20. X equals 20, and if x equals 20, let's just see what happens. If I were to plug in 20 for x, 3 times 20 is 60, 60 plus 5 is 65, 65 degrees and the 65 degrees match, which would mean alternate interior angles were congruent, which forces these 2 lines to be parallel. Okay, and so you're going to see different variations throughout your section assignment. It may give you alternate interior, it may give you corresponding, it may give you consecutive interior, it may give you alternate exterior. It doesn't matter, just make sure you follow those same 4 rules. This one happened to be congruent, so I have the equal sign. Be careful. If I come across one that's consecutive interior, then I would add my 2 angles together, whatever that might be. So for instance, if this 65 had moved here, then I would have consecutive interior angles, and they would be supplementary, which means I'd have the 3x plus 5 plus 65 equals 180. That changes the equation. That's just the oddball in the bunch. Be aware of that one as you move forward. All right, so now let's move on to our proof. Our second example, our last example from this section. In this case, you are given line R is parallel to line S. That's actually shown here in the diagram with these little red arrows. We're actually starting with some parallel lines that are given. Second thing we're given is that angle 1 is congruent or the same as angle 3. That's shown here in the diagram. Those little arches, again, just mean congruent angles. So these have to match, whatever they may be. Our job here is to prove that these two lines, P and Q, sorry if my Q's look weird, but P and Q have to also be parallel to each other. That's our job to prove here. We're going to be able to prove this in 4 steps. Again, the ways you're going to see this in big ideas, the way you might see this on a test or on my final at this point, since that's likely where we'll next see each other, or maybe not see each other, but what you'll next test you'll be doing in my class. So the way you'll be seeing this is you'll be basically given fill in the blanks. In big ideas, you'll have drop-down menus. For my test, it'll be something similar to this. We have a row for claims. We have a row for reasoning. First step, this should be automatic for everyone. It's my given information. I can only start proofs with my given information. So this is, whether or not you understand it, this is something that you can always do. All arguments have to start with my given evidence, my given information. So it's just copy and paste of my given. R has to be parallel to S, and angle 1 has to be congruent to angle 3. Why does that claim have to be true? Because that's my given information. That's what I start with, based on the diagram and based on my given information. Now, with any proof, I'm going to use this claim to build on my next claim. Now, the next claim here is that angle 1 is congruent to angle 2. Our job is to come up with why. What reason makes this true? And we're going to use one of these 2 pieces of information to make this claim. So the one that's going to give this claim credence, what's going to make this true, the fact that angle 1 and angle 2 have to be the same thing, is because of this claim right here. Because R is parallel to S. We started with this. R and S are parallel to each other. Because of that, angle 1 and angle 2 have to be the same. Why? Because they're corresponding same position angles. I'm going to abbreviate right there. That's corresponding angles. Angle 1 and angle 2 are corresponding angles when it comes to R and S. Now, this can be confusing for people because there's a lot going on in this diagram, let's be honest. But if I were to, say, cover up this line P, notice I have 2 parallel lines cut by a transversal. Line Q right there is my transversal, and R and S, which I've just kind of covered up. But R and S are the 2 parallel lines that are going through Q. Now, because 1 and 2 are both top left angles, they are corresponding. And because I started with the fact that R and S are parallel, corresponding angles have to be congruent. Now, you wouldn't have to do this in your proof, but let me just kind of show why can I use corresponding angles, because R and S are parallel to each other. That was what made that part true. Okay. All right. Well, great. Angle 1 and angle 2 now have to match. Perfect. But now what I'm going to be doing is my next step. I'm still not at my finish line. I still haven't shown anything about line P and Q yet. But we're going to use the transitive property to make this next claim. Now, just a little review right here. This is one of the more common reasons to be given in any proof. But transitive property, to remind everyone, is that property: if A equals B and B equals C, then A has to equal C. We're going to use these 2 facts right here. Notice that angle 1 is used in both to connect angle 2 and angle 3. Namely, angle 2 has to be congruent to angle 3. Why? Because if angle 1 and angle 2 match, and angle 1 was already matching angle 3, then these 2 have to be the same. Why? Because of the transitive property. So why does that help me here to my final step? Well, if these 2 angles match, these are what we call alternate interior angles. These are alternate interior angles of the lines P and Q. Because these are alternate diagonal and side